The darkness between the stars is not what it seems. We look up at a night sky filled with points of light, but the true nature of the cosmos is defined by the vast, empty expanses in between, places we call cosmic voids. These are not simple blanks, but realms hiding profound mysteries that unsettle our most basic ideas about reality. Today, we begin a journey through 25 of the universe's greatest enigmas, a journey that will challenge everything you think you know about space. You will gain a completely new perspective on the structure of reality itself. We will confront a sphere of nothingness so large it defies physics, and ask if the faint echo of the Big Bang is pointing toward a parallel universe. What does the great cosmic emptiness make you wonder about most? Our first stop is a place of staggering emptiness, a hole in the universe so vast it should not exist. This is the Boötes Void, a spherical region of space nearly 330 million light-years across. To grasp that scale, picture our entire Milky Way galaxy as a grain of sand. Now imagine a sphere so enormous it could contain thousands of those grains. Yet within the Boötes Void, astronomers have found only a handful of galaxies, perhaps 60, scattered in that incomprehensible volume. Where we would expect to see tens of thousands of glittering islands of stars, there is almost nothing. It is a true desert, a cosmic vacuum so profound it has earned the nickname the Great Nothing. Its very existence shakes the foundations of cosmology. Our standard model of the universe describes a web-like structure with galaxies strung along dense filaments of dark matter surrounding these vast empty bubbles. But the Boötes Void is not just a bubble, it is a chasm. It is far too large and far too empty to fit comfortably into our simulations of how the cosmos should have evolved after the Big Bang. It defies the odds, like rolling a die and getting the same number 1,000 times in a row. So what could have created such a monumental absence? One theory suggests it is simply a statistical fluke, a rare but possible gap in the grand tapestry. Perhaps the dark matter web in that region was unusually sparse, leaving no scaffold for galaxies to form. But the scale makes even this explanation feel inadequate. Other ideas venture into far more speculative territory. Could the void be a region where a different set of physical laws apply? A place where gravity or the nature of dark energy operates by alien rules, preventing matter from coalescing? Or, most mind-bending of all, is the Boötes Void the imprint of a collision with another universe? In some multiverse theories, our cosmos could have brushed against a neighboring bubble universe in the distant past. That titanic interaction might have swept the region clean, pushing matter away and leaving behind this eerie, empty scar. The Great Nothing, then, might not be an absence at all, but evidence of a presence we cannot otherwise see. It stands as a silent, daunting question mark at the very beginning of our list, a reminder that the universe's deepest mysteries are often written in the spaces between the stars. That profound emptiness of the Boötes Void challenges our models of cosmic structure. But what if a void could also leave a distinct mark on the very first light of creation? This brings us to our second mystery, one that involves a ghostly chill in the ancient afterglow of the Big Bang. We call this the cosmic microwave background, or CMB. It is the oldest light we can see, a faint whisper of radiation that has been traveling for over 13 billion years, filling the entire universe. This afterglow is remarkably uniform, a nearly perfect thermal blanket. Yet upon this smooth canvas, astronomers have found a strange and significant blemish, a region in the constellation Eridanus that is noticeably colder than its surroundings. This is the famous CMB cold spot. For years, its existence puzzled scientists. Then they found a possible culprit, a corresponding structure in the more recent universe, the Eridanus supervoid. This is another colossal region of space, an estimated 1 billion light-years across, that contains far fewer galaxies and clusters than it should. the theory seemed elegant, a cosmic detective story solved. The idea is that as light from the CMB passes through such a vast underdense region on its way to us, it loses a tiny amount of energy. This is due to an effect called the integrated Sachs-Wolf effect. Think of it like climbing out of a deep valley. The light expends energy escaping the void's weakened gravitational pull, causing it to redshift slightly and appear colder to our telescopes. The problem is the math does not add up. The Eridanus supervoid, as immense as it is simply not large enough or empty enough to produce the dramatic temperature drop we observe in the cold spot. The void might explain a small chill, but not this deep freeze. This discrepancy is the heart of the controversy. It means either our measurements of the void are incomplete or something far more exotic is at work. Some physicists propose that the cold spot is not a shadow cast by a void at all, but a direct imprint from the universe's violent infancy. One radical hypothesis suggests it could be the bruise from a collision with another bubble universe during the period of cosmic inflation, when our cosmos expanded faster than light. In this scenario, the collision would have drained energy from that patch of spacetime, leaving it permanently cooler. So we are left with a haunting correlation, a cold spot in the ancient sky that lines up with a great modern emptiness, yet the two do not fully explain each other. Is this a case of cosmic coincidence, a flaw in our understanding of gravity, or is it tangible evidence that our universe once brushed against another? The Eridanus supervoid and its enigmatic cold shadow keep that profound question unsettlingly open. This unsettling possibility of a cosmic collision imprinted on the sky forces us to ask a deeply personal question. Where are we in all this vast emptiness? The answer is more surprising than you might think. We are not floating on some grand, crowded galactic boulevard. Evidence now suggests we may be living inside one of these voids ourselves. Welcome to the KBC void, named for the astronomers who identified it. This is a local underdensity, a bubble of relative emptiness that stretches for over 2 billion light-years. And our own Milky Way galaxy sits not on the edge but remarkably close to its center. Picture our cosmic address not as a bustling city center, but as a quiet, spacious suburb in an exceptionally large and quiet neighborhood. This realization turns a fundamental assumption of cosmology on its head. For decades, astronomers have operated on the Copernican principle, the idea that we do not occupy a special or privileged place in the universe. We assumed that on very large scales, the cosmos looks roughly the same everywhere. The KBC void challenges that. It suggests our local region is significantly less dense than the cosmic average. Why does this matter for more than just cosmic geography? It has profound implications for how we measure the universe's most vital statistic, the Hubble constant. This number describes how fast the universe is expanding. For years, we have had two primary ways to measure it. One method looks at the ancient light of the CMB, the cosmic microwave background. The other uses relatively nearby objects like pulsating stars and exploding supernova as cosmic mile markers. These two methods, however, keep giving us different answers. They disagree by a small but stubborn amount. This discrepancy is called the Hubble tension, and it is one of the biggest headaches in modern cosmology. It could mean there is something fundamentally wrong with our standard model of the universe. Here is where our local void offers a potential solution. If we are sitting inside a giant cosmic bubble that is emptier than average, it changes the local landscape of gravity. Matter outside our void pulls on us slightly differently. This affects the apparent speeds of the nearby galaxies we use to calculate the expansion rate. In essence, we have been trying to measure the universe's expansion from inside a hole without fully accounting for the shape of the hole itself. Correcting for our place inside the KBC void could bring those two conflicting measurements into closer agreement. It would mean the tension is not a flaw in our physics, but a flaw in our perspective. We are not in a special place in terms of importance, but we may indeed be in a special place in terms of geometry, a quieter pocket that has subtly skewed our view of the entire cosmos. The void around us is not just empty space, it is a lens through which we see everything else, and we are only now beginning to understand how it distorts our vision. That idea of our view being distorted by emptiness becomes even more profound when we realize we might be missing entire structures in the sky. Our latest mystery proves the cosmos still has the power to shock us with the utterly unknown. In 2019, astronomers working with a new generation of radio telescopes stumbled upon something that should not be there. They found faint, perfect circles of radio wave emission hanging in deep space, visible only to radio eyes and completely invisible in optical, infrared, or X-ray light. They named them quite simply odd radio circles, or ORCs. These are not small curiosities. Each one is a behemoth, often spanning 1 million light-years or more, large enough to swallow several galaxies like our Milky Way whole. They float in the intergalactic void like ghostly halos, immense and enigmatic. What could possibly create such vast, symmetrical, and ephemeral rings, visible in only one specific slice of the electromagnetic spectrum? The leading theories are as dramatic as the objects themselves. One compelling idea points to a cosmic catastrophe of unimaginable scale, the merger of two supermassive black holes at the hearts of colliding galaxies. When such monsters finally spiral together and coalesce, they can send a titanic, spherical shockwave screaming through intergalactic space at nearly the speed of light. This shockwave, plowing into the thin gas between galaxies for millions of years, could energize it to glow in radio waves, leaving behind a perfect, expanding shell, a fossilized echo of that violent union. Another hypothesis looks to a different kind of galactic violence, a starburst galaxy. In a frenzy of star formation, powerful galactic winds can blow a colossal bubble of hot gas out into the void. The edges of this bubble, as it expands and cools, might also produce the radio ring we see. Yet, for some ORCs, even these cataclysmic explanations feel insufficient. Their symmetry is too perfect, their isolation too strange. This has opened the door to more speculative and frankly thrilling possibilities. Could an ORC be the mouth of a spacetime wormhole, its circular glow the result of radiation emitted from hot gas being funneled through a cosmic shortcut? Or, perhaps most haunting of all, might we be looking at a signature on a scale beyond comprehension, the lingering energy of a technological civilization that learned to harness the power of its entire galaxy? A so-called Kardashev Type 3 civilization could, in theory, create an emission structure of this staggering size. While this remains the least likely and most extraordinary explanation, its mere consideration underscores how deeply mysterious these circles are. They are a reminder that the voids are not just empty, they are a canvas, and we are only now beginning to see the first brushstrokes of phenomena we do not yet have the language to describe. These ghostly circles in the radio sky challenge our sense of cosmic solitude, but an even more fundamental assumption is being tested by the motion of the universe itself. We have long believed that on the grandest scales, the cosmos expands in a stately, uniform manner, with every galaxy drifting apart from every other like raisins in a rising loaf of bread. There should be no preferred direction, no universal current. This principle of isotropy is a cornerstone of modern cosmology. Yet, a startling discovery has revealed what appears to be a vast, mysterious drift in the fabric of space. Astronomers call it dark flow. By studying the subtle distortions in the cosmic microwave background, scientists have detected something extraordinary. Hundreds of massive galaxy clusters, each containing thousands of galaxies, are not just moving with the expansion. They are all streaming in the same specific direction at astonishing speeds, over 2 million miles per hour. It is as if a cosmic river, invisible and irresistible, is pulling them along. This is not a local phenomenon. The scale of this coherent motion is staggering, spanning billions of light years. The force required to create such a vast, aligned current is beyond anything we can account for within the observable universe. There is no known supercluster, no concentration of dark matter powerful enough to generate this pull. So what could possibly be tugging on so much of the cosmos? The most profound explanation points to something literally outside our reality. The leading hypothesis suggests that dark flow is the gravitational imprint of a massive structure that lies beyond the cosmic horizon, in a region of space-time that inflated away from us during the Big Bang and is now forever out of reach. Imagine our observable universe as a bubble in a vast, frothing sea of other bubbles, a multiverse. If another bubble universe existed extremely close to ours in that sea, its immense mass, though separate, could exert a gravitational influence that reaches across the void, tugging on everything within our cosmic bubble. We would feel the pull but could never see the source. This idea shatters the cosmological principle. It suggests that the universe is not uniform and isotropic on the largest scales we can measure. There is a directionality, a lopsidedness imposed by something from outside. The controversy is intense, with some scientists proposing alternative explanations involving rare, giant voids or subtle measurement errors. But if dark flow is real, its implications are universe-altering. It means our cosmic home is not a self-contained island, but a raft caught in a current whose origin lies in the unknowable beyond. We are not just floating in a void, we are being pulled through it toward a mystery that exists outside the confines of space and time as we know them. This mysterious cosmic current pulls our gaze across the void, but as we look deeper, we find an even stranger form of order etched into the fabric of reality itself. We now encounter a discovery so bizarre it seems like a glitch in the simulation, a cosmic conspiracy written in the spin of the universe's most powerful engines. When astronomers studied the light from quasars, the brilliant cores of distant galaxies powered by voracious supermassive black holes, they noticed something impossible. These quasars are separated by billions of light years, distances so vast they should have no knowledge of each other's existence. According to everything we know, the universe on such grand scales should be isotropic, meaning it should look the same in every direction with no preferred alignment. The rotation axes of these black holes, which dictate the direction of the immense jets of matter they fire into space, should be pointed randomly like countless spinning tops tossed across a floor. Yet that is not what the data shows. Over truly cosmic distances, the rotation axes of these quasars appear to be aligned with each other. They are not perfectly lined up, but the correlation is far stronger than random chance could ever produce. It is as if an unseen hand, in the first moments of creation, gave a subtle, uniform twist to the seeds that would one day grow into these monstrous black holes. This alignment presents a profound puzzle. What force could possibly coordinate the spin of objects separated by voids so immense that not even light has had time to travel between them since the universe began? The coordination had to be baked in at the beginning. One compelling theory points to the influence of primordial magnetic fields. These would be magnetic fields generated in the universe's first split second, woven into the fabric of space-time itself during the inflationary epoch. As the cosmos expanded, these fields could have stretched across the entire observable universe, creating a subtle, grid-like structure that guided the collapse of the first giant clouds of gas, imparting a preferred direction of spin to the black holes that formed within them. Another, even more exotic possibility involves cosmic strings. These are theoretical, one-dimensional defects in space-time, remnants of the universe's violent birth, thinner than an atom but of infinite length and unimaginable density. A network of such strings stretching across the cosmos could have acted like the grooves on a record, channeling matter and influencing the angular momentum of forming structures on a universal scale. The most unsettling implication, however, is that this alignment might point to a literal axis of the cosmos. It hints that the universe itself may have a preferred direction, a fundamental lopsidedness that breaks the principle of isotropy we hold so dear. This would mean that on the largest scales, the universe is not the same in every direction. There is a grain to reality, a cosmic texture we are only now beginning to feel. The aligned quasars are like compass needles, all pointing toward a truth we cannot yet see, suggesting that the emptiness between them is not a formless void, but a structured medium imprinted with the memory of its own explosive birth. The eerie alignment of quasars hints at a hidden structure in the void, but what if that structure is not just made of geometry, but of missing matter? We face a cosmic accounting error so large it involves half of everything we are made of. We call this the missing baryon problem. Baryons are the particles that make up all the normal, tangible stuff in the universe, the protons and neutrons in stars, planets, and our own bodies. Cosmologists can calculate with great precision how much of this ordinary matter should have been created in the Big Bang. When they add up all the matter we can see in every star, every galaxy, every speck of dust, they come up staggeringly short. We have only found about half of what the math says should be there. It is as if you meticulously budgeted your salary, but your bank account only ever shows half the money. The other half has simply vanished. This is not dark matter, that mysterious, invisible substance that holds galaxies together. This is the regular stuff, the atoms themselves, that have gone missing on a universal scale. So where did it all go? The leading suspect is hiding in plain sight, or rather, in the dark side of the cosmic voids. Scientists believe the missing baryons are not in bright, dense objects, but spread out in an incredibly diffuse, superheated fog that permeates the vast spaces between galaxy clusters. They call this the warm-hot intergalactic medium, or WIM. Imagine the cosmic web not as a structure of glowing galaxies, but as a scaffolding of faint, incredibly hot gas. These are filaments of million-degree plasma, so thin that in a volume of space the size of your average room, you might find only a single atom. This makes them nearly impossible to see directly. They do not glow with visible light, only emitting a faint whisper of X-rays or subtly distorting the light of distant quasars that pass through them. Finding the WIM is like trying to map a network of fine, hot wires by watching how they make distant streetlights shimmer on a foggy night. The evidence, however, is mounting. By combining data from multiple X-ray and ultraviolet telescopes and studying the absorption lines in the light of countless distant quasars, astronomers are beginning to trace the outline of this hidden architecture. They are finding that the great voids are not completely empty. They are filled with this tenuous, seething ocean of normal matter, a ghostly residue of the universe's formation that never quite collapsed into stars. This discovery closes a fundamental gap in our cosmic ledger. It tells us that half the universe's normal matter was never truly missing. It was just hiding in the hardest place to look, in the immense, hot silence between the galaxies. The voids, therefore, are not just absences. They are reservoirs holding in an almost invisible form the very atoms that could have built 1 trillion more stars, but instead chose to linger in the dark, connecting everything in a web of faint, superheated threads. That hidden web of hot gas connects the cosmos, but it also exerts a powerful pull on everything within it, including us. Our entire galaxy, along with its neighbors in the local group, is not drifting aimlessly. We are on a journey swept along by titanic currents in the gravitational sea. For decades, astronomers tracked this motion and found we are all streaming toward a specific point in the constellation Centaurus at a staggering speed of over 1 million miles per hour. The source of this immense pull was dubbed the Great Attractor. The mystery was profound because the Great Attractor lies directly behind the obscuring dust and stars of our own Milky Way's galactic plane, in what astronomers call the zone of avoidance. It is like trying to see a mountain range through a permanent, dense fog. As our observational tools, particularly in X-ray and radio wavelengths, pierced this veil, the picture became clearer and even more immense. The Great Attractor is not a single monstrous object. It is a gravitational focal point, the heart of the Laniakea supercluster, a vast continent of galaxies 100,000 times more massive than the Milky Way. Our entire local group is just a distant suburb falling toward this cosmic metropolis, but the story of our motion has a second, equally powerful character. For every great pull in the universe, there must be a corresponding push, and scientists found it in the form of a profound emptiness. This is the dipole repeller. While the Great Attractor pulls us from one direction, the dipole repeller is a vast, underdense region, a cosmic void of staggering scale that pushes us from the opposite side. How can nothingness push? Think of gravity not just as a force that pulls, but as the shape of space-time itself. A region dense with matter, like the Great Attractor, creates a deep gravitational well. We slide down its slope. Conversely, a vast void, like the dipole repeller, is like a broad, flat plateau or even a gentle hill. The relative lack of matter there means the gravitational pull from that direction is weaker than from the denser regions surrounding it. We are not so much pushed away from the void as we are pulled less hard by it, causing us to flow toward the greater concentration of mass. Our cosmic trajectory is the result of this grand imbalance. We are in a gravitational tug-of-war between an immense overdensity and an immense underdensity. And the landscape is even more complex. Beyond the Great Attractor, at an even greater distance, lies the Shapley supercluster, the most massive concentration of matter in our local universe. Its colossal gravity is also tugging on us, adding its weight to the pull. So our motion is a sum of these forces, fleeing the repelling void while being drawn toward the combined might of Laniakea and Shapley. This reveals a universe where motion is dictated not just by the bright islands of galaxies, but by the dark, empty expanses between them. The voids are not passive backgrounds. They are active players, their profound absence shaping the flow of the cosmos as definitively as any supercluster. The pull of the Great Attractor and the push of the dipole repeller define our local motion. But what if our entire cosmic neighborhood is also distorting our view of the universe's ultimate fate? This brings us back to that critical discrepancy, the Hubble tension, a crack in the foundation of modern cosmology that might find its solution in the void around us. The problem is stark and growing. When we measure the universe's expansion rate by looking at the ancient cosmic microwave background, we get one very precise number. When we measure it using relatively nearby celestial mile markers like Cepheid variable stars and Type 1, a supernova, we get a different, faster number. The two methods representing the early universe and the local universe stubbornly refuse to agree. This is not a small statistical fluke. It is a persistent and significant tension that suggests something fundamental in our standard model of cosmology, known as lambda CDM, might be wrong or incomplete. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant as we assume, or perhaps our measurements are being skewed by something in our own cosmic backyard. This is where void cosmology offers a compelling, elegant explanation. Recall that we may be living inside the KBC void, a local bubble of space that is significantly emptier than the cosmic average. Gravity works differently inside such a void. The relative lack of mass inside the bubble means there is less gravitational pull holding the local fabric of space together compared to the denser regions outside. As a result, space inside our local void wants to expand faster. The galaxies we use as local mile markers are feeling this enhanced local expansion, like buoys bobbing on an inflating raft that is itself stretching more quickly than the wider ocean. Our local measurement, therefore, picks up this boosted expansion rate. Meanwhile, the cosmic microwave background measurement reflects the average expansion rate of the entire universe, a rate dictated by the global density of matter and dark energy, largely unaffected by our specific underdense pocket. If we are indeed inside a sizable void, the two measurements would naturally differ. The tension would not be an error in physics, but an error in perspective. We have been trying to calculate the universe's average speed from inside a cosmic fast lane. This idea, however, comes with profound implications. It directly challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. If a local void can be large and deep enough to explain the Hubble tension, it means the universe is lumpier than we thought. Matter is not smoothly distributed. We live in a notable underdensity, a special place in terms of geometry, if not importance. Furthermore, it questions the uniformity of dark energy. Our standard model treats dark energy as a constant, a property of empty space itself. But if voids expand faster, does dark energy behave differently inside them? Could it be stronger in emptier regions, driving them apart more vigorously? This would mean dark energy is not a simple cosmological constant, but something more dynamic, interacting with the structure of the cosmos. The void, therefore, is more than an empty space. It is a laboratory. Its apparent emptiness might be the key to unlocking the true nature of cosmic acceleration, forcing us to ask whether the universe's fate is written in the galaxies or in the vast, accelerating emptiness between them. The universe's expansion rate is not the only measurement that could be skewed by our place in a void. Some of the most energetic particles in existence carry a similar puzzle, one that pits the emptiness of space against the very laws of physics. This is the mystery of the GZK cutoff, named for the scientists Grison, Zatsepin, and Kuzmin. Their prediction is based on a simple, brutal fact of intergalactic travel. The cosmos is filled with the faint afterglow of the Big Bang, the cosmic microwave background. This sea of ancient photons is not completely harmless. For a proton traveling across the universe at nearly the speed of light, these photons are like a dense fog of tiny, high-speed bullets. When an ultra-high-energy cosmic ray proton, one with energy millions of times greater than anything produced in our largest particle colliders, collides with one of these CMB photons, it undergoes a catastrophic loss. The proton essentially shatters, creating a shower of lower energy particles in a process called photomeson production. This means there should be a strict distance limit, a cutoff, for how far these ultra-high energy particles can travel. Any proton from a source farther than about 150 million light-years away should have been slowed down by this photon fog long before it reaches us. Its energy should be sapped, falling below the theoretical GZK limit. Yet our detectors on Earth, like the Pierre Auger Observatory, have occasionally recorded cosmic rays that smash right through this predicted ceiling. These particles arrive with energies so absurdly high they seem to have ignored the cosmic traffic jam entirely. They act as if they traveled through a much emptier universe than the one we think we live in. This is where the voids offer a compelling escape clause. What if these ultra-high energy particles did not travel a uniform, foggy path? What if their journey was mostly through the profound emptiness of a cosmic void? In a region like the Boötes Void, the density of the CMB photons is the same, but the crucial factor is distance. If a proton could chart a course that kept it within an immense void for most of its journey, it would have far fewer collisions over that vast distance. It could, in effect, sneak through the universe using the empty corridors, arriving at our doorstep with its extreme energy intact. The void acts as a cosmic freeway, a low interaction zone that preserves these rare messengers. But there is another, stranger possibility. Perhaps the voids are not just emptier of matter, but contain something else that alters the rules. Could there be extremely subtle fields or unknown low-energy phenomena within these expanses that subtly change how particles like protons interact with the CMB? Maybe the voids are not pure vacuums, but arenas for physics we have not yet described, where the relationship between matter and radiation is slightly different. The defiance of the GZK cutoff, then, is a double-edged clue. It either reveals that the cosmic voids are even more transparent than our best models suggest, creating pristine highways across the universe, or it hints that the great emptinesses are not empty at all, but filled with a subtle, active presence that rewrites the journey of the universe's most powerful particles. These cosmic freeways of emptiness are not completely deserted. Within the profound darkness of the deepest voids, astronomers have found solitary travelers, isolated islands of stars adrift in a sea of nothing. These are the void galaxies, and their existence tells a story of cosmic solitude that defies our expectations. While the Boötes Void may contain only 60 galaxies where thousands should be, those few it does hold are fascinating anomalies. Imagine a single spiral galaxy like our Milky Way, but one that has spent its entire multi-billion-year life almost completely alone, with no neighboring galaxies for millions of light years in any direction. This is the reality for a void galaxy. It is a galactic hermit forming and evolving in near-total isolation, free from the gravitational harassment, collisions, and cannibalism that define life in the crowded urban centers of galaxy clusters. This extreme environment has produced galaxies that seem frozen in a more primitive state. Contrary to what you might expect, many void galaxies are not stunted or withered by their isolation. They are often richer in the cold, neutral hydrogen gas that fuels star formation. Their stellar populations can appear older and more tranquil, with fewer of the violent, dramatic bursts of star formation seen in cluster galaxies. They are like quiet, rural villages that have preserved their old ways, compared to the chaotic, rapidly evolving megacities of the cosmic web. This presents a direct challenge to standard models of galaxy formation. We thought that a galaxy's evolution was primarily driven by its interactions, by mergers with other galaxies that trigger activity, feed central black holes, and reshape structures. A void galaxy experiences almost none of that. Its evolution is dictated almost entirely by internal processes, the slow, steady consumption of its own gas reserves. Studying them is like running a controlled experiment on galactic life, removing the variable of a busy environment to see what a galaxy does on its own. What we see are objects that often appear less evolved, holding onto their primordial gas longer and forming stars at a more leisurely and steady pace. Their supermassive black holes tend to be quieter, not fueled by incoming material from collisions. This suggests that the frenetic, violent life in clusters might be the anomaly, a disruptive influence that accelerates evolution in ways that are not the cosmic norm. The void, in its profound quiet, may allow for the purest, most undisturbed form of galactic life. These lonely giants force us to ask which is more representative of a typical galaxy story, the chaotic dance in the clusters or the solitary, slow-burning existence in the void. Their very existence and their strange, preserved nature implies that the emptiness of space is not just a backdrop, but a defining cradle for a different kind of cosmic life. These lonely void galaxies exist in profound silence, but that silence is sometimes shattered by the most violent and mysterious signals in the universe. Streaking across billions of light-years of emptiness comes a pulse of pure energy so intense it outshines entire galaxies in a fraction of a second. This is a fast radio burst. An FRB is a brief, brilliant flash of radio waves, often lasting just milliseconds, that appears without warning from the deep cosmos. Their origins are one of astronomy's greatest modern puzzles, and the vast cosmic voids may hold a key to understanding them. When an FRB travels through space to reach our telescopes, it does not pass through a perfect vacuum. It traverses a sea of electrons, the diffuse plasma that fills the space between galaxies. These electrons act like a subtle cosmic prism, slowing down the lower frequency radio waves just a bit more than the higher frequency ones. By the time the burst reaches us, its frequencies are spread out or dispersed. This dispersion measure is a critical clue. It tells astronomers the total number of electrons the signal encountered along its path. Think of it like listening to a sound echo through a long, foggy canyon. The way the echo is distorted tells you something about the density and length of the fog it traveled through. By carefully analyzing the dispersion of an FRB, scientists can essentially weigh the invisible material between us and the source. This allows them to map the distribution of that tenuous intergalactic plasma, confirming the existence of the WHIM, that warm, hot intergalactic medium, and measuring its density in the great voids the burst passed through. Each FRB becomes a single, brilliant flashlight beam, illuminating the dark, filamentary structure of the cosmic web for one fleeting instant, but the voids may play an even more direct role. Some of the most intriguing FRBs are the repeaters, sources that fire off multiple bursts over time. Several of these have been traced back to host galaxies that reside in surprisingly low-density environments on the fringes of cosmic voids. Why would that be? One possibility is one of cosmic acoustics. The relative quiet and emptiness of a void could provide a clearer channel for these signals. With less turbulent plasma and fewer interfering magnetic fields to scatter or distort the radio waves, a burst originating in or passing through a void might arrive at our telescopes in a purer, more detectable state. It is like hearing a whisper clearly across a silent, empty hall versus trying to hear it in a noisy, crowded room. The void acts as a natural amplifier of clarity. Then there are the non-repeating bursts, the one-off cataclysms. For these, the void itself could be more than just a quiet channel. It could be the stage for the catastrophe. If the source of such an unimaginable energy release is something truly exotic, like the collapse of an ancient, primordial star made of exotic matter, or the snapping of a cosmic string, those theoretical defects in space-time, then the empty expanse of a void might be the most likely place for such an event to occur undisturbed. In the crowded galactic clusters, such a signal might be muddied or obscured. In the pristine emptiness of a void, the burst could announce itself with shocking clarity. So our fast radio bursts messages from the voids or messages clarified by them. Either way, these milliseconds of cosmic violence are doing more than just baffling us. They are turning the greatest emptinesses into tools, using their profound nothingness to help us map the invisible something that holds the universe together, and perhaps to reveal the locations of its most unimaginable explosions. These fleeting bursts of radio energy are messengers from the void, but they are newcomers compared to the ancient imprints written into the emptiness itself. To understand the true nature of a cosmic void, we must travel back to the very beginning of everything, to a time before time, when the entire observable universe was smaller than a single atom. In that searing, unimaginable moment, the cosmos was not smooth. It was a chaotic quantum foam, a turbulent sea of virtual particles flickering in and out of existence. These are quantum fluctuations, tiny, spontaneous variations in energy that are a fundamental feature of reality at the smallest scales. For a fleeting instant, one region of this primordial soup might have had a minuscule fraction more energy than the region right next to it. Another spot might have had a fraction less. Normally, these differences are utterly insignificant and vanish almost instantly, but then cosmic inflation happened. In a fraction of a second, the universe underwent a period of exponential expansion, inflating from a quantum speck to a macroscopic size faster than the speed of light. This dramatic stretching did something extraordinary. It took those infinitesimal quantum jitters and magnified them to astronomical proportions. A region that started with a tiny overdensity of energy after inflation became a slightly denser patch of the young universe. A region that began with a tiny underdensity, a minuscule deficit of energy, became a slightly emptier patch. These imperfections became the seeds for all future structure. Over billions of years, gravity acted as an amplifier. The slightly denser regions pulled in more and more matter from their surroundings, growing into the great filaments, clusters, and superclusters of galaxies we see today. And those initial under-dense regions, they were the seeds of the cosmic voids. As matter flowed toward the growing, denser areas, it drained away from these emptier patches, leaving them behind to expand and become the vast, barren deserts we now observe. This means the Boötes Void, the Eridanus supervoid, the KBC void, every great emptiness we have discussed, is not a random accident. It is the magnified fossil of a quantum fluctuation from the universe's first trillionth of a second. The void is a direct imprint from the quantum birth of reality, stretched to a scale of hundreds of millions of light years. This transforms our understanding of these empty spaces. They are not mere absences, they are cosmic archaeology sites preserving a record of physics at energies so high we could never hope to recreate them in a particle collider on Earth. By meticulously mapping the sizes and distribution of voids throughout the universe, cosmologists are essentially reading the quantum fingerprint of inflation. The pattern of voids and filaments is a snapshot of those first quantum tremors, frozen in time and expanded to the grandest canvas imaginable. So when you look up at the dark spaces between the stars, you are not just looking at nothing. You are gazing at the magnified echo of the universe's first moment, a quantum whisper that has grown into a cosmic shout, defining the architecture of everything that is, by showing us the profound legacy of what is not. The quantum origins of voids reveal a cosmos built on ancient, amplified whispers. But could those immense, quiet spaces also be hiding something far more deliberate? This brings us to one of the most speculative and fascinating mysteries on our list, a profound thought experiment that merges cosmology with our deepest questions about life in the universe. We call it the Fermi paradox, the stark contradiction between the high probability of alien civilizations and the complete lack of evidence for them. One compelling answer suggests we are simply not looking in the right places or for the right things. Perhaps the most advanced civilizations are not broadcasting from the crowded galactic centers we typically scan. Perhaps they have moved to the cosmic suburbs, to the voids. Consider the incentives for a truly advanced galaxy-spanning intelligence, what we term a Type 3 civilization. Their primary goals would likely involve long-term survival and energy efficiency. The galactic core and the dense filaments of the cosmic web are dangerous neighborhoods, bustling with lethal radiation from supernova, perilous close encounters with other stars, and the threat of gamma-ray bursts, the universe's most powerful explosions. A void, by contrast, is the ultimate gated community. It is a region of profound quiet and stability with vast distances between any celestial hazards. The ambient temperature is lower and the cosmic background radiation is easier to manage. For a civilization that has mastered stellar engineering, the void offers a clean, controllable slate. But the appeal goes beyond mere safety. Energy is the ultimate currency. A Type 3 civilization would need to harness the total energy output of its entire galaxy, likely by constructing something like a Dyson sphere, a megastructure enveloping a star to capture its power. In a crowded galactic disk, such constructions could be obscured by dust and light pollution from billions of neighboring stars. In a void, however, a single, isolated star surrounded by a vast energy-harvesting structure would stand out with stark clarity against the utter blackness unless the civilization did not want to be seen. This is the second, more chilling possibility. A truly advanced intelligence might prioritize stealth. The void provides the perfect cover for activities that wish to remain hidden. Its immense scale and our relative lack of detailed surveys make it the ideal cosmic wilderness in which to disappear. Their megastructures might be designed to emit minimal waste heat in the spectra we commonly observe or to mimic natural phenomena. They might use the void's emptiness as a heat sink, radiating their excess energy in directions we cannot detect, or even using the structure of space itself in ways we cannot yet comprehend. Their entire existence could be folded into the background static of the universe, invisible by design. So, when we gaze into a profound emptiness like the Boötes Void, we are confronted with an unsettling duality. We see a fossil of quantum creation, a natural consequence of cosmic inflation. But we must also wonder if, within that same darkness, we are looking at something else entirely, a chosen refuge, an engineered preserve, or a hidden metropolis of intelligence so advanced it has become one with the void. The silence we perceive may not be the silence of absence, but the silence of something that has learned perfectly how not to be heard. That profound silence, whether natural or engineered, is not a static feature of the cosmos. The voids themselves are changing, expanding at a rate that may hold the key to the universe's ultimate fate. Within their immense emptiness, we find a unique laboratory for studying the most mysterious force in existence, dark energy. This enigmatic pressure, making up about 70% of the universe's total energy budget, is what drives the acceleration of cosmic expansion. We know it is there because everything is flying apart faster and faster, but we have almost no idea what it actually is. The frustrating part is that its effects are subtle and compete with the powerful grip of gravity. In the dense urban centers of galaxy clusters, gravity's pull is so strong that dark energy's repulsive push is almost negligible on local scales. It is like trying to measure a gentle breeze inside a hurricane, but step into a cosmic void and the balance of power shifts dramatically. Here, the density of matter is extraordinarily low. There is very little gravitational pull to counteract. In this near-perfect vacuum, the repulsive effect of dark energy becomes the dominant force. It is not that dark energy is stronger in a void, it is that it has less competition. As a result, the walls of a void, the thin membranes of galaxies that define its borders, are pushed apart faster than regions filled with matter. The void does not just expand with the general flow of the universe, it actively balloons outward, its emptiness growing more profound as dark energy overwhelms the feeble gravity within it. This makes voids the universe's most sensitive dark energy detectors. By meticulously mapping the shapes, sizes, and distributions of voids across different epochs of cosmic time, astronomers can take the universe's pulse in a new way. Imagine bubbles in a pot of water beginning to boil. As the heat increases, the bubbles grow larger and their walls thin and stretch. Dark energy is the heat under our cosmic pot. By measuring how void shapes evolve, whether they become more spherical or distorted, and how quickly their walls recede from one another over billions of years, we can measure the strength and nature of that accelerating pressure with unprecedented precision. This could answer the most pressing question in cosmology: is dark energy a simple cosmological constant, an immutable property of empty space itself, as Einstein once suggested? Or is it something dynamic, a field that changes strength over time, perhaps even weakening or strengthening? If voids are expanding at a rate that cannot be explained by a constant dark energy, it would force a revolution in physics. The great emptinesses, therefore, are far more than passive holes. They are active, evolving experiments. Their accelerating growth is a direct readout of dark energy's work, offering us a clear view into a force that remains invisible everywhere else. By staring into the void, we might finally see what is pushing the entire universe apart. Dark energy's accelerating push might be thinning the walls of the cosmic voids, but within those expanding deserts, astronomers are finding ghosts. These are not the brilliant quasars or the fleeting radio bursts of our earlier mysteries. These are phantoms of a different kind, vast, shapeless, and almost invisible. We call them ultra-diffuse galaxies, and their presence in the void is a quiet, profound enigma. An ultra-diffuse galaxy, or UDG, is a cosmic paradox. It can be as wide as our own Milky Way, spanning 100,000 light-years from end to end, yet it contains only about 1% of the stars. Imagine taking all the glittering structure of our spiral galaxy, every brilliant arm and central bulge, and stretching it out into a formless, tenuous cloud of faint starlight so dim it nearly vanishes against the blackness of space. Spotting one is an extraordinary feat, like discerning the outline of a city at night from 1,000 miles away, using only the combined glow of its streetlights. While some of these ghostly galaxies have been found lurking in the crowded environments of galaxy clusters, often stripped and harassed by their neighbors, it is their discovery in the profound isolation of cosmic voids that raises the deepest questions. How does something so large, so fragile, and so seemingly empty come to exist in a place where there is almost nothing to build with? The void is a nursery of scarcity. Gas is sparse, and gravitational interactions that trigger star formation are rare. Standard models of galaxy formation suggest that in such an impoverished environment, you would expect only small, dwarf galaxies to slowly eke out an existence. An ultra-diffuse galaxy defies that logic. Its immense size implies it once had access to a vast reservoir of primordial gas, enough to create a grand structure, but for some reason, that gas never efficiently turned into stars. This leads to two compelling and opposing theories about their nature. The first casts them as cosmic failures. In this scenario, a UDG is a galaxy that started with all the right ingredients but never got the recipe right. Perhaps its gas was too hot from the beginning, or it was infused with turbulent energy that prevented it from cooling and collapsing into dense star-forming clouds. It is a galaxy that, for billions of years, has been stuck in a state of arrested development, a sprawling, faint testament to a process that never quite ignited. The second theory, however, suggests these ghosts are not failures at all, but rather galaxies cloaked in extraordinary armor. This idea posits that ultra-diffuse galaxies are, in fact, dominated by immense spherical halos of dark matter. This dark matter provides the gravitational scaffolding that holds their faint stars in such an extended configuration. The dark matter halo might be as massive as the one surrounding the Milky Way, but for reasons unknown, it attracted and retained far less of the normal star-forming gas. In this view, a void UDG is not a failed galaxy, but a dark matter fortress that simply never lit up its battlements. This distinction is crucial because it forces us to confront fundamental gaps in our understanding. If they are dark matter rich, their existence in voids challenges models of how dark matter itself is distributed. We thought the most massive dark matter halos naturally drew in the most gas to form the brightest galaxies. A void UDG appends that, suggesting dark matter can assemble into vast structures that, by cosmic chance, remain almost empty. If they are dark matter poor failures, then their sheer size and survival are the puzzles. How does such a flimsy, star-poor structure hold itself together for billions of years without a massive dark matter anchor to protect it from being torn apart by even the faint tidal forces of the void? Each ghostly galaxy drifting in the emptiness is therefore a single, haunting day to point in a much larger argument. Are we looking at the skeletons of galaxies that never lived, or the invisible frames of galaxies that chose to live in the dark? Their faint light is a whisper from the void, asking us which force truly sculpts the cosmos, the bright fury of star formation, or the silent, unseen grip of dark matter. Ghostly galaxies whisper of unseen forces, but the oldest light in the universe carries a more direct message about cosmic structure. The cosmic microwave background is not the perfectly uniform blanket we once believed it to be. Beyond the famous cold spot, other large-scale anomalies in this ancient afterglow hint at a universe that is fundamentally lopsided. When scientists decompose the CMB map into its fundamental components, like breaking down a musical chord into individual notes, they find something strange in the lowest, deepest notes. The quadrupole and octupole moments, which describe the largest possible temperature variations across the sky, show unexpectedly low power. It is as if the universe is missing its deepest bass notes, making the cosmic symphony sound oddly muted on the grandest scales. Even more curiously, the patterns of hot and cold in these particular moments appear to be aligned with each other along a specific axis in space, a feature some scientists have dramatically nicknamed the axis of evil. This alignment suggests a preferred direction, a cosmic grain that violates our assumption of isotropy, the idea that the universe should look the same in every direction. What could possibly impose such a directionality on the entire observable universe? The answer may lie in the immense, asymmetric geometry of the cosmic web itself. Imagine our observable universe not as a perfectly smooth sphere, but as a bubble embedded within a larger, lumpy cosmos. If one hemisphere of our bubble is bordered by an exceptionally vast and deep supervoid, while the opposite hemisphere brushes against an unusually dense supercluster, this imbalance would leave an imprint. As the CMB light from the dawn of time traveled through these vastly different cosmic neighborhoods on its way to us, it would be subtly altered. The great void, with its weaker gravity, would cause a slight blue shift, making that region appear warmer. The supercluster, with its stronger pull, would cause a slight redshift, making its region appear cooler. This could create the kind of large-angle, dipolar pattern we see in the low-order moments, effectively painting a temperature map of the universe's large-scale structure onto the first light. The axis of evil, then, might simply be the axis pointing from the greatest nearby underdensity to the greatest nearby overdensity. Our entire view of the primordial universe is being lensed or subtly distorted by the colossal emptinesses and concentrations of matter that surround our local cosmic bubble. This means the CMB is not just a baby picture of the universe, it is a picture that has been framed and slightly warped by everything that has happened since. If these anomalies are real and not statistical flukes, they force a monumental rethink. They suggest that our observable universe is not a fair sample of the whole. Its geometry is imprinted by structures so vast they shape the background radiation itself, with cosmic voids acting as one of the primary sculptors of this ancient light. The silence of the voids, it seems, echoes all the way back to the beginning of time. The ancient light carries imprints of vast emptiness, but the void itself may hold another, more active force woven through its expanse. We find magnetism in the deepest cosmic deserts. Even in regions nearly devoid of galaxies and stars, astronomers have detected the faintest whispers of magnetic fields, stretching across millions of light years. This is a profound puzzle. We understand how a star or a planet can generate a magnetic field through the churning of conductive material in its core, a process called a dynamo. But how does a near-perfect vacuum, a cosmic void, become magnetized? These fields are incredibly weak, billions of times fainter than a common refrigerator magnet, yet they are ubiquitous, a subtle cosmic fabric. Their origin points back to the universe's youth and the turbulent birth of the first structures. One leading theory begins not in the voids but in the spaces between them. In the early universe, as the first stars and galaxies ignited, they did so with violence. Supernova explosions and powerful jets from active galactic nuclei sent shockwaves rippling through the primordial gas. These shockwaves, like cosmic tsunamis, could have generated weak magnetic fields through a process called the Biermann battery effect, where differences in temperature and pressure in a swirling plasma spontaneously create electrical currents and magnetism. These infant fields would have been vanishingly faint, but the cosmic web provided the amplifier. As matter flowed along the filaments of the web, funneling toward the dense nodes where clusters would form, it also stretched and sheared these primordial magnetic field lines. Think of it like pulling on a strand of cosmic taffy embedded with iron filings. The stretching action aligns and intensifies the magnetic signature. This is where the voids play their crucial, counterintuitive role. They are the negative space in this grand process, As galaxies and clusters formed in the dense regions, they ejected material and energy through winds and explosions. This enriched material, carrying those stretched magnetic fields, was often blown out into the surrounding voids. The vast, empty expanses then became a dumping ground and a diffusion chamber for magnetism. Over billions of years, these fields, though weak, could have spread through the void carried by the tenuous plasma that does exist there. The voids themselves might also be sites of a slower, more subtle dynamo. Even the sparse gas in the walls and filaments defining a void's border is in motion, stirred by the gravitational pull of the structures around it. This incredibly slow, vast turbulence could further twist and amplify magnetic fields over cosmic time. So the faint magnetism we detect in the great nothing is likely a fossil record, a ghostly echo of the universe's first energetic outbursts, stretched and dispersed by the very architecture of the cosmic web. Solving this mystery means understanding how a fundamental force of nature became a background feature of empty space, a silent, invisible energy woven into the fabric of the void itself. Magnetism may thread the voids, but gravity is the true architect of these empty spaces. Yet, what if we have misunderstood the architect's most fundamental rule? Our 19th mystery confronts a radical possibility that the profound emptiness of a cosmic void is not a simple absence of matter, but a region where the force of gravity itself plays by a different set of rules. This is the heart of the phantom void hypothesis, and it challenges the very foundation of modern cosmology, Einstein's theory of general relativity. For nearly a century, general relativity has been our gold standard for understanding gravity, describing it not as a force but as the curvature of spacetime by mass and energy. It works spectacularly well, predicting everything from the bending of starlight to the orbit of Mercury. But on the vast scales of galaxies and galaxy clusters, a problem emerges. The visible matter alone does not provide enough gravity to explain how these structures hold together or move as they do. Our solution for decades has been dark matter, an invisible, mysterious substance that provides the extra gravitational glue. But a small, persistent group of physicists proposes a different path entirely. They suggest we do not need dark matter if we simply revise our laws of gravity. This idea is known as modified Newtonian dynamics, or MUND. In its simplest form, MUND proposes that gravity does not weaken as quickly with distance as Newton or Einstein predicted, especially in regions where the gravitational field is extremely weak, like the outer edges of galaxies or, crucially, in the deep cosmic voids. This is where the phantom void hypothesis takes shape. Imagine our local KBC void again, that immense bubble of relative emptiness we may call home. In the standard model, its underdensity is just that, a lack of stuff. Its gravitational effects are straightforward, or so we think, but under a theory like MUND, the story changes dramatically. In the profoundly weak gravitational environment of a void's interior, the modified equations of MUND predict that gravity could behave in an enhanced, non-linear way. The emptiness itself might generate a stronger gravitational influence than general relativity would allow. From our perspective inside the void, this extra gravitational push or pull would appear exactly as if there were extra, invisible matter present. In other words, the void would phantom matter. It would mimic the effects of dark matter without any dark matter actually being there. The void is not just empty, it is a gravitational illusion. This makes cosmic voids the ultimate cosmic laboratories for testing gravity itself. In the crowded, high-gravity environments of galaxy clusters, the predictions of general relativity and MUND can be difficult to disentangle from the effects of hypothetical dark matter. But in a void, the signal is cleaner. The gravitational field is so feeble that any deviation from Einstein's predictions would stand out like a single wrong note in a silent room. Scientists are now using sophisticated maps of the cosmic web and the subtle motions of the few galaxies within voids to look for these deviations. They are asking, do the walls of voids expand and evolve exactly as general relativity plus dark matter predicts? Or does their behavior better match the predictions of modified gravity? The answer could reshape our understanding of the universe. If the phantom void hypothesis holds, it would mean that the great cosmic deserts are not merely testing grounds for dark energy, but for gravity itself. The apparent emptiness would be a cosmic sleight of hand, a region where the fabric of space-time behaves in a way we never anticipated, making nothingness feel as heavy as a galaxy. It forces a humbling question: are we searching for invisible matter to fill a void? Or is the void itself showing us that our map of reality is missing a fundamental dimension? Gravity's rules are tested in the emptiness, but the grandest challenge to cosmic uniformity may be written in light itself, a line of brilliant beacons that seems to stretch across a quarter of the observable universe. This is the Huge Large Quasar Group, or huge LQG, a discovery so immense it strains the limits of what we thought possible. Astronomers mapping the sky found not one or two, but 73 quasars, the luminous hearts of ancient galaxies, aligned in a structure that spans an almost incomprehensible 4 billion light-years. To grasp that scale, if you could travel at the speed of light, it would take you 4 billion years just to go from one end of this group to the other. This is not merely a large cluster, it is a cosmic continent, a gathering of the universe's most powerful engines on a scale that directly confronts a bedrock principle of cosmology. That principle is homogeneity, a key part of the cosmological principle. It states that on the very largest scales, beyond about 1 billion light-years, the universe should look roughly the same everywhere. Matter should be evenly distributed, with no single structure dominating the cosmos. The theoretical maximum size for any coherent structure is thought to be around 1.2 billion light-years. The huge LQG shatters that limit, being more than 3 times larger. It is as if surveyors, expecting to find rolling hills, suddenly stumbled upon a mountain range that stretched from the Earth to the Moon and back 1,000 times over. Its very existence suggests the cosmic web, the tapestry of voids and filaments, might be woven with threads of a grandeur we never dared to predict. The debate within the astronomy community is intense and fundamental. Is the huge LQG a true, physically connected structure, a titanic filament in the cosmic web where quasars just happen to light up like street lamps along a single, impossibly long cosmic highway? Or is it a staggering illusion, a chance alignment of separate quasars that lie at vastly different distances, only appearing to be linked from our particular vantage point in the cosmos? This second possibility is crucial. Our telescopes see the universe in 2 dimensions, a flat sky. Determining the true 3-dimensional distance to an object like a quasar is complex and can have margins of error. If some of these 73 quasars are actually much closer or farther away than we estimate, the apparent group could dissolve into a random scattering, a cosmic mirage. But if it is real, the implications are universe-altering. A structure of this scale would mean that the universe is not as smooth as we believed, even on its grandest canvases. It would imply that the processes of the early universe, the gravitational collapse seeded by those primordial quantum fluctuations, operated with a coherence and power that our current models do not account for. The great voids would then be the negative spaces in an even more magnificent and complex painting, their emptiness defined by the borders of structures so vast they redefine large. The cosmic web would have a superstructure, an architecture within an architecture. This discovery forces us to look at the map of the cosmos with new eyes. Are the largest voids we know, like the Boötes Void, merely the rooms inside a single, even larger chamber of the cosmic labyrinth? Does the huge LQG trace the outline of a filament so immense that it makes the Great Attractors supercluster look like a local neighborhood? The existence of such a group suggests that the universe, in its infancy, may have imprinted patterns with a longer wavelength than we thought possible, patterns now revealed only by the rare, brilliant beacons of quasars that dot its length. It is a reminder that our cosmic maps are still being drawn, and the largest features may still be hidden in plain sight, waiting for us to understand the scale of our own ignorance. That immense quasar group stretches the very definition of a cosmic structure, but the universe also contains a far more subtle and perfect pattern, a fossilized echo of its own birth cries. In its first few 100,000 years, the cosmos was not a quiet, empty place. It was a seething, opaque plasma, a roiling soup of particles and light so dense that photons could not travel freely. Within this primordial fluid, gravity was constantly trying to pull matter together into clumps, but there was a powerful opposing force, the intense radiation pressure from the blinding light. This created a cosmic tug-of-war where regions of slightly higher density would contract under gravity, only to be pushed back out by the radiation pressure, creating spherical sound waves that propagated outward through the hot plasma. These were not sound waves as we hear them, but massive pressure waves expanding at over half the speed of light. Then, around 380,000 years after the Big Bang, the universe cooled enough for atoms to form. The particles and light suddenly decoupled and the cosmos became transparent. Those traveling pressure waves froze in place, their final positions imprinted forever in the distribution of matter. This is the phenomenon of Barrian acoustic oscillations. Think of it like dropping a pebble into a still pond. The ripples expand outward in perfect circles. If the pond were to instantly freeze solid at that exact moment, you would have a permanent record of the ripple, a frozen wave with a very specific distance from the center to its peak. The early universe was filled with countless such pebble drops, each quantum fluctuation creating a frozen ripple. The result is a cosmic fingerprint, a preferred scale woven into the fabric of reality. This scale, the distance those sound waves traveled before the universe became transparent, is about 500 million light-years. It acts as a standard ruler etched across the cosmos. We can see its imprint today by looking at the clustering of galaxies. If you take a vast survey of the universe, you will find that galaxies are slightly more likely to be separated by this specific distance, a statistical echo of those ancient frozen waves. But here is where the voids become absolutely crucial. They offer the cleanest, most powerful way to measure this standard ruler. Imagine those frozen ripples again. The peak of the wave, where matter piled up, corresponds to the dense walls of galaxies we see in the cosmic web. The trough of the wave, the region the wave evacuated, corresponds to the centers of the cosmic voids. The distance from the center of a void to the surrounding shell of galaxies is directly tied to the size of that primordial sound wave. By meticulously mapping the three-dimensional shapes and sizes of millions of voids and measuring the typical distance from a void's empty heart to its densely packed walls, astronomers are taking the universe's most precise measurements. They are using the voids as negative templates to trace the outline of that 500 million light-year ruler. This is revolutionary for cosmology. Because we know the true physical size of this standard ruler from the physics of the early universe, we can compare it to how large it appears to us at different distances, and thus at different epochs in cosmic history. If a void from 10 billion years ago appears a certain angular size in our telescopes, and a similar void from 5 billion years ago appears a different size, we can calculate exactly how much the universe has stretched in that time. This gives us an incredibly precise history of the expansion rate, independent of other methods like supernova. Voids, therefore, are not just empty spaces to be studied. They are precision calibration tools. Their predictable geometry, sculpted by those ancient sound waves, allows us to measure the influence of dark energy with unprecedented accuracy, tracking how its repulsive push has changed over billions of years. The great silence of the void holds within it a perfect, resonant note from the universe's first song, and by listening to its echo, we are learning to measure the expansion of everything. That frozen echo of the universe's first sound waves gives us a perfect ruler, but what of the rulers themselves, the objects we use to measure the cosmos? Some of the most extreme and violent objects ever created might not stay in the crowded galactic neighborhoods where they were born. They are cosmic runaways ejected into the great dark. When a star many times more massive than our Sun reaches the end of its life, it does not go quietly. It dies in a cataclysm known as a core collapse supernova, an explosion so brilliant it can outshine an entire galaxy. In that final, violent instant, the star's core, crushed under its own immense gravity, collapses into an object of almost unimaginable density, a neutron star. A single teaspoon of its material would weigh as much as a mountain. Some neutron stars are born with magnetic fields trillions of times stronger than Earth's, becoming magnetars, the universe's most powerful permanent magnets. But this birth is rarely symmetrical. The explosion can be lopsided, firing jets and ejector more powerfully in one direction. Like a rifle recoiling after a shot, this asymmetry delivers a tremendous kick to the newborn stellar remnant. This natal kick can propel the neutron star or magnetar out of its stellar nursery at speeds exceeding 1,000,000 miles per hour, fast enough to escape not just its own star cluster, but the gravitational pull of its entire host galaxy. Once free, it becomes a lone wanderer sailing into the intergalactic void. Picture a city-sized diamond, denser than any material possible on Earth, spinning hundreds of times per second and possessed of a magnetic field so intense it could wipe the data from every credit card on a planet halfway across the galaxy. Now imagine that object drifting in perfect, perpetual darkness, with no nearby star to illuminate it, no planetary system to influence, just the cold, near-perfect vacuum of a cosmic desert for millions or billions of years. How would such an isolated monster behave? Its primary power source is its own incredible spin and its decaying magnetic field. A magnetar's field is so unfathomably strong it stresses the very fabric of its solid crust, causing starquakes, seismic events that crack its surface. These quakes can release colossal bursts of gamma rays and X-rays in an instant. If one of these eruptions happened while the magnetar was adrift in a void, the signal would travel unimpeded across the emptiness. It could appear to us as a short, hard gamma ray burst with no visible host galaxy, a ghostly flash from nowhere. Furthermore, the magnetosphere of a rapidly spinning, highly magnetized neutron star is a cauldron of physics. It is theorized that the twisting of magnetic field lines could generate incredibly powerful radio wave emissions. Some scientists speculate that certain non-repeating fast radio bursts, those brilliant millisecond flashes, could be the death cries of a distant magnetar, perhaps one that has been wandering the voids for eons and finally experiences a catastrophic instability. The signal, traveling through the pristine, low-density channel of a void, would arrive sharp and clear. These isolated stellar corpses offer a terrifying and fascinating possibility. The voids may not be completely inert. They could be haunted by these dark, ultra-dense ghosts, each one a relic of a stellar catastrophe that occurred billions of years ago in a galaxy now far, far away. Their occasional, violent outbursts would be the only signs of their existence, brief flares that illuminate the cosmic emptiness before it returns to perfect dark, reminding us that even nothingness can have a memory, and that memory is written in the language of shattered stars. These dark, wandering remnants are the ghosts of stellar history, but the void itself may be preserving an even older story. While the dense cores of galaxy clusters are dynamic, violent places where matter is constantly recycled and polluted, the cosmic void is a sanctuary of stillness. Its profound emptiness is not just a spatial feature, it is a temporal one. Because the density of matter is so incredibly low and gravitational interactions are so feeble, the physical processes that drive cosmic evolution move at a glacial pace here. While galaxy clusters are frenetic cosmic cities evolving rapidly through mergers and collisions, a void is a forgotten wilderness, changing almost imperceptibly over billions of years. This makes it a potential time capsule, a region where conditions may remain closer to those of the early universe than anywhere else we can observe. The chaotic, polluted environments of galaxy clusters are like bustling archaeological sites where layers of history have been scrambled and mixed by countless events. The void, by contrast, is a perfectly sealed dig site where the artifacts of cosmic dawn might lie undisturbed. What could such a pristine environment preserve? One of the most tantalizing possibilities is primordial gas. In the dense filaments of the cosmic web, gas has been cycled through multiple generations of stars. When stars die in supernova, they seed their surroundings with heavy elements like carbon, oxygen, and iron, the very elements that make up planets and life. This process, called chemical enrichment, pollutes the interstellar medium. But in the deep void where star formation has always been rare, there may still exist vast, diffuse clouds of gas that have never been touched by a supernova. This gas will be composed almost entirely of hydrogen and helium, the pristine elements forged in the first few minutes after the Big Bang. Finding and studying such a cloud would be like discovering a vial of the universe's original atmosphere, unchanged for over 13 billion years. Its chemical signature would give us a perfect baseline, revealing the exact conditions before the first stars began their alchemical work. Beyond the gas, the void's isolated galaxies themselves could be living fossils. We discussed ultra-diffuse galaxies as potential failures or dark matter fortresses, but their quiet evolution also makes them candidates for preserving ancient stellar populations. A void galaxy that formed its stars early and then was left in peace might contain a disproportionate number of population 2 stars, the ancient metal-poor stars that formed from only slightly enriched gas. In the deepest voids, we might even dream of finding a surviving relic from the very first generation of stars, so-called population 3 stars. These hypothetical giants, hundreds of times more massive than our Sun, were made of pure hydrogen and helium. They are thought to have lived fast, died young, and seeded the universe with its first heavy elements. None are believed to exist today, as they would have consumed their fuel in mere millions of years. But if one formed in the extreme isolation of a void, away from the triggers that spur later star formation, could a tiny, dim remnant of that first generation still smolder in the darkness? It is a long shot, but the void is the only place we might reasonably look. By studying the oldest stars in the quietest galaxies within the emptiest places, we are effectively using the void as a lens to peer further back in time than any telescope alone could manage. The void's slow motion grants it a unique form of clarity. The light that reaches us from its depths is less likely to be distorted by gravitational lensing from intervening mass, and its signals are less contaminated by the radio chatter of countless nearby galaxies. It offers a cleaner, quieter channel to the past, so when we map a great void, we are not just charting an absence. We are opening a cosmic time capsule, one that may hold, in its profound silence and pristine conditions, the untold story of how a smooth, hot, young universe became the structured, star-filled cosmos we see today. The void is not empty of history, it is saturated with the oldest kind, waiting in the dark for us to learn how to read it. The pristine time capsule of the void offers a glimpse into the universe's raw origins, but it also invites a far more speculative question about the nature of reality itself. Could the profound emptiness of cosmic voids be a clue that we are living inside a simulation? This is the simulation hypothesis, a modern philosophical idea that suggests our entire universe, with all its galaxies, stars, and planets, might be an artificial construct, a kind of ultra-advanced digital reality. From this perspective, the properties of cosmic voids take on a fascinating new meaning. They could be seen not as natural features, but as optimization code. In any complex simulation, processing power is a finite resource. Rendering every cubic light year of a universe with perfect, particle-level detail would be computationally absurd. A far more efficient design would be to concentrate processing on the interesting parts, the galaxies where complex physics, chemistry, and potentially even conscious observers are at play. The vast, nearly empty cosmic voids would be the perfect place to cut corners. Instead of simulating trillions of scattered atoms and subtle fields with high fidelity, the simulation could simply render these regions as low-detail backgrounds, vast tracts of simplified space where the rules are approximated or streamlined to save cycles. The observed properties of voids seem to oddly support this idea. Their sheer scale and remarkable emptiness could be interpreted as a designer's choice to minimize rendering load. The fact that voids often have simple, bubble-like shapes, unlike the chaotic complexity of galaxy clusters, fits the notion of a basic, low-polygon fill. Even the apparent uniformity of the cosmic microwave background within voids could be seen as a default texture, a placeholder skybox for the empty sectors of the simulation. The arguments against this, however, are grounded in the very physics the voids help us test. Scientists point out that voids are not truly empty or simple. They contain the diffuse whim threaded by magnetic fields, and their evolution is governed by the complex interplay of dark energy and gravity. They are integral to the cosmic web, their formation a natural outcome of inflation and gravitational collapse. In other words, voids behave exactly as we would expect them to in a real, physical universe following known, if incomplete, laws. They are not glitches or simplifications, but coherent structures that provide crucial tests for our models. Furthermore, if this were a simulation, why would the programmers leave in such glaring cosmic mysteries as dark matter and dark energy? Would that not be inefficient or sloppy coding? The counter-argument from simulation proponents is that these unsolved puzzles might be intentional, placed there to see if we, as simulated entities, can discover the limits of our programmed reality. Or perhaps they are simply artifacts, the equivalent of texture pop-in or rendering errors at the edges of the high-detail zones. Ultimately, the simulation hypothesis is untestable with our current science. It resides in the realm of philosophy, not physics, yet it adds a captivating meta-layer to our contemplation of the void. When we stare into the Boötes Void, we are confronted with two equally profound possibilities. We are either looking at a magnificent fossil of quantum creation, a natural cathedral of absence shaped over 13 billion years by fundamental forces, or we are peering into a region of the simulation where the resolution drops, where the underlying code of reality becomes just a little more transparent, a quiet corner of the cosmos where the background processes of existence are momentarily exposed. This duality makes the void the ultimate Rorschach test for our understanding of reality. Its silence speaks volumes, but what it says depends entirely on what we believe about the nature of the cosmos itself. The profound silence of a void may be a glimpse of the future, the ultimate destination of everything we see. Our final mystery does not ask what the voids are, but what they will become as we peer into the two most chilling forecasts for the cosmos. The first is a slow, cold fading, the second a violent, final shattering. Both end with the void as the only survivor. The most widely accepted forecast is the heat death of the universe. Picture the expansion continuing forever, driven by dark energy. Galaxies will drift apart until each island universe is alone in an ever-darkening sky. One by one, stars will exhaust their nuclear fuel and wink out, leaving behind cooling embers, white dwarfs and neutron stars that will fade to black over trillions of years. The last light in the cosmos will vanish. Even the mightiest structures, supermassive black holes, are not eternal. Through a process called Hawking radiation, they slowly leak energy, evaporating over unimaginable timescales. In perhaps 10 to the 100 years, a number so vast it has no meaning, the last black hole will pop out of existence in a final, silent flash. What remains is a cosmos stretched to its limit, a near-perfect vacuum at a temperature barely above absolute zero. It is a state of maximum entropy where energy is uniformly spread out and no work can be done, no structure can form, no memory can be kept. This is the heat death, a cold, dark, and eternal equilibrium. The cosmic voids of today are merely the early stages of this process, the first quiet rooms in a mansion that will eventually become entirely empty. Yet there is a more dramatic and far more terrifying possibility. What if dark energy is not constant? What if its repulsive strength grows stronger over time? This leads to the Big Rip scenario. In this forecast, dark energy becomes so dominant that it overwhelms every binding force in the universe, not just the expansion of space between galaxies. First, the cosmic web itself would be shredded. Galaxy clusters, then individual galaxies, would be torn apart as the space between their stars expands faster than gravity can hold them together. Solar systems would be next, planets ripped from their stars. In the final, horrific moments, the expansion would accelerate to infinity. The fabric of space-time would tear at a local level. Stars and planets would be ripped apart, then the very atoms that compose them. The nuclei of atoms would be shredded, and finally, space-time itself would be torn asunder in a catastrophic singularity. The universe would end not with a whimper, but with a literal rip in the fabric of reality. In both of these ultimate fates, the void wins. In the heat death, it is a quiet, cold, and eternal void of near-perfect nothingness. In the Big Rip, it is an active, violent void that consumes all structure before itself potentially dissolving. This transforms our understanding of these great emptinesses. They are not just places in our universe, they are a preview of the universe's final state. Every void we map, every great nothing we stare into is a prophecy. It shows us the end of all stories, the silence after all sound, the darkness after all light. The cosmic void is both the oldest imprint from the quantum dawn and the inevitable future written into the expansion of space itself. It is the beginning and it is the end. The journey through these 25 mysteries reveals a cosmos utterly transformed. We began by confronting the sheer scale of the Boötes Void, a great nothing so vast it defied explanation. We felt the chill of the cosmic microwave background's cold spot, a ghostly imprint perhaps left by a collision with another universe. We discovered our own place within a local void, a quiet bubble that may be distorting our entire view of cosmic expansion. From the ghostly halos of odd radio circles to the mysterious drift of dark flow, we saw that emptiness is not passive. It is threaded with magnetic fields, pierced by ultra-high-energy cosmic rays, and illuminated by the brilliant, fleeting flashes of fast radio bursts that use the void as a cosmic messenger. We met the solitary void galaxies frozen in time, and the phantom ultra-diffuse galaxies, ghosts that question the role of dark matter. We traced the origins of these great emptinesses back to quantum whispers from the first instant of creation, magnified by inflation into the architecture of the cosmic web. We pondered whether voids could be refuges or hiding places for intelligence beyond our imagining, and saw how they act as pristine laboratories, testing the nature of dark energy and even the fundamental laws of gravity itself. From the staggering scale of the huge, large quasar group to the perfect frozen echo of Barrian acoustic oscillations, we learned that voids are the universe's most precise measuring tools. We envisioned runaway magnetars, dark stars adrift in the eternal night, and considered the void as a cosmic time capsule, preserving the pristine conditions of the primordial universe. We even dared to ask if these profound emptinesses might hint at a simulated reality. And finally, we peered into the far future where the void stands as both the beginning and the end, the cold fate of heat death or the violent finale of a big rip. Through it all, one truth has emerged with crystalline clarity. The cosmic void is not nothing. It is a dynamic, evolving, and deeply informative component of reality. It is a sculptor, a lens, a laboratory, and a record. It holds the keys to understanding dark energy, dark matter, gravity, and the very origin of structure itself. The next time you gaze up at the night sky, do not just look at the points of light. Let your eyes rest on the dark spaces in between. See them for what they truly are, not as mere emptiness, but as the dominant feature of our universe, filled with mystery and pregnant with answers we are only beginning to seek. Which of these 25 mysteries of the void fascinates you the most? Do you find the phantom pull of dark flow most compelling, or the silent testimony of the aligned quasars? Share your thoughts below, and if you are hungry to explore more of the universe's greatest secrets, be sure to subscribe. Our journey through the cosmos has only just begun.